Got about a minute 30 left, minute 20.
Sure.
Super excited.
Yeah, me too.
Let's have fun. Keep your hands and feet inside the car at all times.
I did a lot of smiling too.
Yeah. Always enjoy it. Going live in 7.
Okay.
Welcome back to SparkCon 2020 as we review some of the top experts and topics in the field of oil and gas. We want to make sure that the knowledge management systems and the information that you have helps you succeed and deliver results in your business. And today we're going to be talking to Vatsal Shah and improved ground investigations for pipelines and linear construction. A lot of very important topics that you need to understand in your business to be successful. Welcome, Vatsal, and thank you so much for being here. Look forward to your presentation.
Thanks for having me, Russ. Looking forward to presenting here.
You bet. Everybody at SparkCon 2020, look forward to this amazing presentation, and thank you so much for being here. Thanks, Vatsal. I'll check you in on Q&A. We'll have Q&A at the end, and if you have any questions, please drop them in the chat to make sure that we have an opportunity to answer your questions today. Take it away, Vatsal.
Thank you, Russ. As Russ mentioned, I really appreciate everyone's time this early afternoon to go through a very important topic, I think, in the oil and gas industry and just for linear construction in general. I'm a civil engineer by training and by background, but I have a strong emphasis in geotechnical engineering, which is the study and engineering of the subsurface conditions. That's rock and soil and everything else that sits beneath our feet. We know that when we do large linear construction projects, some of the biggest risk comes from ground risk, and that's just ground risk due to the unknowns in the subsurface conditions. When you're working on oil and gas specifically, you have long stretches of alignment where you might have a steep slope. You might go through areas that have karst or shallow rock, and the cost of blasting or sinkhole remediation or even slope rehabilitation becomes a very expensive proposition. So trying to focus on some of your planning dollars up front will really help you in the long term in helping to reduce risk, but not only reduce risk, but also to help make better decisions as you move forward through your construction and operation periods. So that's the emphasis of today's presentation, just improved ground investigation techniques. We typically look at investigating the underground by a series of test pits or soil borings, and I want to introduce some new tools to our toolbox here so we have some other options for us when we go through this planning process. So today's agenda, I want to discuss geophysics. And what geophysics is the non-invasive study of the ground, looking to make better focused decisions so we can spend our investigation dollars much better in other locations. So we'll go through when and why do we use it. We'll go through a few primers, how geophysics are used. We'll take a deep dive into two of the main topics that we use, and that's MASW, multi-channel analysis of surface waves, and ERI, electrical resistivity imaging. And we'll get into that in a little more detail. So we'll do a deep dive into that topic. And we'll also go through just reviewing these geophysical results for energy projects, specifically for linear construction, and how we can make sense of that information for our planning process. So before we start, I work at a firm called Mott MacDonald, and safety is our culture. So I want to start our presentation off with a quick safety stop. I know a lot of us are working from home here, and working from home has different challenges from working from the office. Just one of the big challenges I'm sure we're all going through is work from home fatigue sometimes. We've had a couple months to set up our desk spaces, but just a reminder that working from home, sitting on a couch can be comfortable, but it's really important to have the right ergonomics. So having a desk space that you're working from, having the right monitor set up, having your hands and wrist support as you go through, just taking the right time to focus on your safety at home. When you're working at home, also, take breaks and walk around. Use coasters. You don't spill anything inadvertently on your desk. Keep a neat desk and just keep your routine about yourself. Mental health is as important as physical health. So I wanted to make sure we had a quick moment on safety before we started here. So our first topic, geophysical methods. When and why do we like to use them? As I mentioned earlier, the traditional method for ground investigation tends to be test pits, soil borings, invasive ground investigation techniques. So when do we use something like geophysics? Geophysics is used when we have subsurface conditions that we may want to investigate further, potentially shallow rock, sinkholes, mines, any sort of geologic conditions, steep slope areas that might have underground voids or shallow rock, or even wet springs and surfaces. It's great to use for difficult to access sites. So when we have difficulty bringing a soil boring rig up a slope, across the wetlands, down a 2-3 mile corridor, geophysics can be helpful because it helps you to identify and access difficult sites. It's fantastic for linear construction, what we're talking about today, pipelines and cables and large sites, because you're able to study a large portion of a site versus focusing on a small 1 or 2 inch diameter hole in the ground. It also helps too when you're dealing with permit challenges. And permit challenges meaning if you happen to have wetlands on a site, if you happen to have the inability to access using large equipment, geophysics can be helpful from that purpose too. So why do we use it? Again, it's non-invasive. It's a quick method to pre-screen for geologic risk. So we can help to find out, do we have shallow rock on a site, or how deep is that rock? Is that rock rippable? Do we happen to have a sinkhole? Do we happen to have concerns of a slide happening beneath us? So once we were able to do that, geophysics helps us to focus on where should we spend our investigation dollars. If you have a 3 or 4 or 5 or 20 mile long corridor, it's difficult to do a soil boring every 500, 600 feet. And even that distance apart doesn't give you the resolution that you need to make decisions moving forward for risk planning, for ground risks. So what you may do is you might do geophysics over a large area, then focus on that small portion, that 1 mile stretch of the alignment. They may want to do a few more rock probes or soil borings, or do some geotechnical borings to investigate karsts or anything like that. Once you've identified your risk areas, then you focus on spending your dollars for your investigation techniques. But they're not just used for focusing our investigation. Our geophysics are great also for design parameters. When we're looking at structural design, it helps us to identify shear wave velocity, which gives us the seismic site class for structural design. It helps identify rippability for rocks. If you're looking at, do we happen to have shallow rock across the section of the alignment? Is that rock rippable? And we're looking at electrical resistivity testing and imaging. You also get indirectly through it the 4-point winner, which is a standard electrical resistivity testing that we do for substation and grounding design. So we'll go into a little bit of a primer, different topics that we have. So as I mentioned before, geophysics are non-destructive, they're efficient, they're cost-effective, and when coupled up with traditional investigation techniques like soil borings or test pits, they really do create a more comprehensive look at the ground. And what does a more comprehensive look give us? It gives us more confidence, helps to minimize risks, because risk is never ever disappearing, right? Risk is always there. It's how we manage and transfer risk between either the contractor, the designer, the contract itself. How we manage that risk between those different pieces is how we're going to look at ground investigation concerns. So conventional investigation techniques, what we're seeing here in front of us is a rock cut. On the bottom, you can see a roadway. You see guardrails that are spaced every 6 or 7 feet apart. So you see about 45 feet of alignment between those areas. And at the front here, you see a 30-foot cut. And now the 30-foot cut, if you were to look at it using traditional techniques, you see these vertical striations or lines in the cut going up and down. You'll see about 40 of these lines going up and down. Those represent a 2-inch diameter hole. Now those 2-inch holes were used for rock blasting. We drilled the hole, we put our charge in, we shot our charge, and we got this rock face here. but I use it as an example because a 2-inch hole for a rock blast is the same as a 2-inch hole for a soil boring. If I were to investigate this site and I took a boring at the very left portion at station 0, what I would typically see is a straight solid section of rock, 30 feet of nice competent rock. If I were to go towards the more right side and take it towards the 2/3 of this stream here, as I go through, I see a pretty significant section of solid rock. I go into a weathered zone. After the weathered zone, I go into a soil area, open void, followed by rock. And if I do a boring in the very center, I see what seems like mostly soil, a large area of open void, raveling soil, then weathered rock from that point onward. So in this 50-foot area of zone that we have, I can go in between competent rock to very poor, mostly soil, or weathered rock with some soil within it. So that small area gives us a large variation between those two things. Trying to focus our investigation dollars to identify where we have concern areas, and then doing a boring at the very center, at the right of the alignment, that can help us better understand what the risk looks like. When we deal with sinkholes, which happens quite a bit in the Northeast, also down in the South, you get areas that have voids, right? And they can be sinkholes from karst, dolomite, limestone, gypsum. They can be open mined areas if you're working in areas like Pennsylvania, Ohio, West Virginia. And in those circumstances, trying to put your pipeline over a void, trying to investigate a boring, what this is showing us here is if the boring was 1/10 of the site, AS over AC was 1/10 of the site, we would need 16 of those 2-inch diameter borings to identify the size of that cavern. If the cavern was 1/100th of our site, 160 borings. And collectively, if we keep moving forward, if the void was much smaller, we'd need 1,600 borings to identify that location. So trying to go through in conventional methods to find that void or that sinkhole or that mine area with the resolution that you'd get from a boring would take a significant number of borings, would be a long time out in the field, would be a lot of money spent trying to investigate that void. Geophysics helps identify where that boundary might be. That way, once you know where that void is, then you can go in and actually physically do your investigation at that point. So what are we doing in geophysics? Geophysics are actually measuring the contrast between different physical properties. When we mentioned before electrical resistivity imaging, we're measuring the resistivity difference between a gravel or sand and the resistivity difference between clay or silt. Or even if you happen to have a void, the resistivity difference of air or water in that void versus sand or gravel. Both those materials have different resistivities. So by doing our electrical resistivity imaging or geophysics, that difference in resistivities gives us some sort of profile of the ground. Same thing with seismic techniques. In seismic techniques, what we typically see is a resistive difference between the density material. For instance, if you picture in your mind a nice competent piece of rock, competent rock is a nice dense piece. If you were to have a seismic wave or a shear wave or a shock wave with that rock, the shock wave would travel much faster just because you happen to have that denser material. If it was a softer material, if it was a wetter material, if it was a looser material, because it's not as dense, the shock wave may not travel as fast. So that difference in the ability of that wave to propagate and pass through the material, the difference between those velocities gives you a difference or contrast in material type. So that's what geophysics is doing. It's measuring a difference of materials. When we talk about GPR, which is used quite often also, ground penetrating radar, it's looking at a dielectric permittivity. So measuring the difference between that condition of the soil. So there's different types of methods. I mentioned acoustic, seismic, electrical, electromagnetic, different methods that we have. I'm going to focus mostly on method 1 and 2 today, as well as touch upon GPR, ground penetrating radar, which is a pretty often used technique that many of you may have heard of actually. The more boutique methods, potential fields, microgravity, magnetics, I may not get into them, and well logging, again, it's more complex. I'm going to focus mostly today on acoustic and electrical to give you the basic tools that you need for your toolbox. So the first step for us to identify is, what is the objective of our survey? Why are we using them? And is this even worthwhile using? If we're investigating a greenfield site or a site that doesn't really have a lot of geologic risk to it, things like shallow rock, sinkholes or karst terrain, former mined areas, steep slopes, springs, potential historic fill. If we don't have those geologic concerns, the traditional test pit and boring programs will be just fine. They tend to give you a good cross-section of the area and tend to be pretty straightforward in the information that you get. If we're looking at more of the geophysical considerations, things that have ground concern, our first two ideas are what is the budget that we have and what is the actual information we're looking for. So if we're looking for things like shallow rock, you'll see in the slides as we move forward, a certain technique like MASW, multi-channel analysis of surface waves, that gives you a better idea about where the location of shallow rock may be, the density of the rock, and some of the actual material properties. So our survey design might looking for MASW. If we happen to have karst or sinkholes or former mined areas, we may look at designing the survey to focus on those things. We may pick more of the ERI investigation versus MASW. We may also find out that we're in an area that we're underneath a overhead line, or we have a tracer wire in the ground. An electrical resistivity method may not be the right fit for us because we can have some background interference from sources that are on site. So we may be forced to use MASW. So as we go through this process, we're trying to identify what are we looking to find, shallow rock or other geophysical concern, and also what interferences or ideas that we have that may cause our survey to not be successful. After finishing the type of survey that we're looking for, then we get into the more detail. What level of accuracy do we need? Do we have to have it where the survey is looking for depth to rock within plus or minus 10 or 20 feet? Are we looking for sinkholes, just generally a broad brush? Are they in this area or not in this area? Or more of a confirmation or a refutal there? Or do we need to have a level of data which is precise? I have to know the depth of rock within plus or minus 1 or 2 feet, or I happen to know the size of the sinkhole within several feet of my pipeline location. That gets into more detailed. Do we then have to have our LiDAR survey draped over the investigation we cover? Do we have to have position fixing and GPS of all of our locations in the field where we take our geophysical shots? Which also then goes into how we acquire our data, download and back up the data, how we process the data based on the type of information that we need. So I mentioned this earlier, there's different sources of noise and interferences you may have. Geophysical surveys are great, but they're measuring changes in the Earth's properties. So if you're looking at things like MASW, that multi-channel analysis of surface waves at shear wave velocities, what we're seeing is if you happen to have things that can be moving the ground or creating vibrations, nearby roadways, if you happen to have water wave crashings, wind moving around, root vibration. This may seem pretty substantial, but we had a project just a few months ago out in the Pacific Northwest, and we had to actually pull away blades of grass away from the geophones, the sensors, because they were creating a lot of wind, and the wind was knocking around and creating backgrounds in the vibrations of the geophones. So you're looking at what sort of considerations do we have. At the same time, if you're looking at things like electrical resistivity, you'll see at the very top here, the arrows show you the different types of concerns you have. Seismic has, ground movement. Electrical resistivity happens to have overhead lines, tracer wires and cables, metal fences and charged metal utilities and those sort of things. So those sort of noises may change or modify the way that we look at our investigation and our survey type.
Hey, Vatsal, we had a question. I just wanted to point this out, and I think this addresses
Sure.
it, is how does multi-channel analysis how does multi-channel analysis surface waves, MASW, elevate ground stiffness? So that was one of the
Right.
questions we had in here. So,
well, that's a great question there. It measures ground stiffness because it's looking at the density of the material. And the density of material helps give you different material parameters. What's the Poisson's ratio of the material? How fast can the material propagate waves through it? So the faster it can go through, the more dense the material it is. So stiffness is a function of density.
okay, great. Yeah. I hope we answered your question. Also, another question was asked earlier that I think that you may have covered, you might want to expand on, is what are some limitations to geophysical techniques?
Sure. So you might notice before that we're doing things as a non-invasive technique. And non-invasive means we're using sensors on the ground or at the ground and using correlations, things like density. How fast can a wave travel? Now we know that the proof is in the proverbial pudding. If you were to dig a hole in the ground, you see how the ground looks. You dig a test pit, you dig a hole, you open it up, you can see how the ground behaves. So one of the limitations of geophysics is it doesn't directly measure the ground itself. So if you wanted to go out there and take a sample of the material, do a grain size analysis, hey, what's the exact material type? We confirmed it's a sand because I took a sample in the ground with my own eyes, I saw it, I took it to a lab and I tested it. Geophysics, because you're not digging a hole, you're not invasively investigating the ground, you kind of miss some of those things you normally would get. So that's one of the limitations that we have with geophysics.
Got it. Got it.
It's a very good question.
Thank you so much. And the other one, the other question that was asked earlier is what the geophysical methods typically measure. And I think you just pretty much answered that as well. So thank you so much.
Yep. Yeah, they measure a difference in material types.
Yeah. Well, thank you so much. I'll let you continue.
Great questions.
If any questions come up, I'll pop in again.
Fantastic. Well, this is a great deep dive for the question that Melanie asked is how are we actually measuring ground stiffness? Well, the first thing I want to discuss is the different methods we talked about, MASW, electrical resistivity, and some of the more boutique microgravity and GPR. MASW, as I specifically talk about this, it's measuring the shear wave velocity as it travels through a material. Let's break that down a little bit. What we're looking to do is we're taking a 10-pound sledgehammer, right? That sledgehammer actually hits a steel plate on the ground. The steel plate on the ground will then create a shock wave. As I slam the hammer against the steel plate, that sends down a shock wave into the ground that bounces into the ground and off different materials. As it bounces off different materials, it reflects back up to these sensors here. And as it reflects back up to the sensors measure the speed at which that seismic wave comes back at, and that speed is a function of density and stiffness. That's how we're evaluating this thing. So we typically see this helping us investigate down as deep as 100 feet down on the ground. So by doing this sensor, we can get a profile of the soil or rock down to about 100-foot depth. And we can actually make this thing deeper by spacing the sensors apart, or we can bring it shallower by bringing the sensors closer together. And the spacing between the sensors will actually affect the accuracy of our information that we have. So the wider we go, the less accurate we get, but the more coverage or more depth we can get. And the tighter we go with our sensors, the more accuracy we get, but the shallower we get because our sensors are looking at a much tighter spacing at that point. So the shear wave velocity depends on Young's modulus and shear moduli, which are based off of density and stiffness. And once you get to the site, the cost of MASW, once you've mobilized, is usually around $2,500 to $3,500 per day, which is usually the cost of having a soil boring rig out there. But you can typically do 1 or 2 20 or 30-foot borings in a day. You can do a much larger area through MASW techniques, looking at several hundred feet being investigated. So what are we doing specifically? We hit this steel plate in the ground. That steel plate then reflects back the shear wave velocity. It hits the sensors at different times. And we get what we see here on the lower right-hand side, this plot of the ground surface. Now you'll see this old black dot at different locations at 1,000, 1,050, 1,100, and so on. That black dot is the 50-foot spacing between each of the sensors. So what this is doing is it's giving you a one-dimensional slice. And at that slice, we see this sort of plot. This plot shows us that the shear wave velocity, the very top of the plot here, increases, right? It increases with depth. As you go deeper in the ground, the shear wave velocity increases as well. So I do that at each of my geophone locations, and I can create a cross-section. And if I were to connect the dots, hey, where does the 200 foot per second of this location match up with the 200 foot per second at the location next to me, and the geophone next to that, and the geophone next to that? I can create this two-dimensional profile from these 1D slices of what the ground looks like. This is a 30-meter deep profile, or 100 feet, and we see these variety of colors. Now, this might look like it's Greek to everyone on the presentation, but I want to just go through. The legend here shows us that the slower velocities, in blue represented here, the mid velocities in greens, and they get darker as you go towards the reds and blacks. I mentioned earlier that the Higher velocities tend to be for stiffer materials. Stiffer materials mean things like dense rock or weathered rock. The lower materials, things that are blues, tend to be more of the softer clays and the water and the saturated materials. So this profile here is showing us in this 400-foot alignment, which took us probably about an hour to do, this 400-foot swath, we're able to see that the profile has about 20 meters of this overburdened soil. Towards the 300 to 400 meter section of this alignment, it gets softer. As it continues going through, we see it's pretty wetter up here. But if we're looking at things like shallow rock, hey, will we encounter shallow rock in this area? Will we end up seeing concerns about ripping or rippability? Do we have to trench this area? What this is showing us is that usually around 20 meters, we're starting to see this dense material. That's probably the weathered rock zone, the top of the weathered rock. And around 22 and 30 meters deep, that's where some of that shallower rock exists. So if we're looking at the concern of we're going to be going over this 500-foot long or 1,000-foot long or even mile long section of alignment, rather than doing borings every 500 feet along this alignment, which can become difficult or expensive, or having to bring a drill rig up a slope, this helps us look at this profile in a much quicker way. Hey, we don't see shallow rock here. We don't see any voids here. This 400-foot swath is okay. Let's focus our investigation dollars somewhere else where we might have a higher risk potential. So that's what MASW here is doing for us. I mentioned also that there's other applications to it, design applications. You may have seen that the Caterpillar, who makes dozers and excavators, they have the Caterpillar handbook available for free online. And in that handbook is a great resource. It actually has a chart based off different types of Caterpillar equipment. The D8 dozer, for instance, D9, D7, and variety of information, different pieces of equipment. What is the rippability of this rock material? So we measured before the shear wave velocity. And what this is asking us for is, based off of the shear wave velocity, the seismic velocity that we have, they're actually giving you a reference saying if you happen to have a low shear wave velocity and you're dealing with things like sedimentary rock like shale, is it rippable? And this chart is giving you rippable, marginal, or non-rippable. So you can kind of also understand if you have this 400, 500,000 foot long alignment, you collect information in a very quick sense. Hey, is that rock rippable or is it not rippable? And that saves versus having to go through and do a variety of soil borings, take the core, and even soil borings themselves may not give you the true rippability, so to speak, of that rock. So we can use that quite a bit for that location. We also use it for liquefaction assessments. If you're looking at seismic considerations or areas that have liquefaction concerns, we look at it for bedrock mapping, and again, looking at it for soft zones. So here's an application we just had recently. This is for a large site we wanted to look at. Is it able to be developed? Do we happen to have rock that needs to be ripped for cut and fill? And what you see here is there's 12 different dots on this site, right? This multi-acre site, 120 acres. And on that site, for us to do 12 borings may have taken up to 4 to 5 days to investigate each of those borings. Traditional soil boring, collect the soil sample, drill, collect our rock sample. What we did here instead is at these 12 locations, we did 12 individual MASW shots, or MASW survey techniques. And at each location, for instance, location 1 at the upper top side here, you see this plot of velocity with depth. The depth is increasing on the top, velocity is increasing as you go up. You see that the local area here in New York, for instance, happens to have a rock called bluestone rock. Bluestone rock happens to have a shear wave velocity of around 2,500 foot per second. So that's a pretty known criteria for this type of rock here. If we were to take a plot across the area here and draw a line at 2,500 foot per second, where we intersect it is around 17 feet. So looking at this geophysical result, we find that at location number 1, our depth to rock is approximately 17 or so feet. The same happens at location 2, 3, 4, 5, all across. I did number 9 here, for instance. We find that the location at 2,700 foot per second comes out to about 30 feet. And once we have that depth to rock across each of the locations at the site, we can assemble a depth to rock map. So what you see here is an isopleth showing that at the very westernmost portion of the site, the rock is the deepest, and it grades as you go more east. So as you go more east, the rock becomes as shallow as 7.5 feet, but for the most part, rock stays around 10 or so feet below ground surface. So the concern of shallow rock in trenching, the concern of shallow rock for foundations, isn't a concern for the site here. We can continue progressing moving forward, but that's a better use of our investigation techniques. Just for cost sense, the investigation would have been about $25,000 to do traditional soil boring investigation for 12 borings across the site, for the lab testing for it, for the engineering design associated with it, and the lab testing. And the schedule may have taken between 3 to 4 weeks to identify this sort of concern at the site. The geophysics were done for about $13,000, but half the cost. Information was available within about a week, and similar information was able to help us move our planning forward. Rock wasn't there at the site. Traditional foundations could be used. No rock reparability needed. Continue moving forward. So we're able to use that money saved and focus that towards de-risking another portion of the project. So I mentioned earlier, another technique we want to discuss is ERT, electrical resistivity tomography. And ERT, if you're familiar with the electrical resistivity testing, the 4-point winner, it's just a 4-point winner array just on steroids. It's instead of having 4 different injection points, you can have as many as 96 different injection points. Now, as I mentioned earlier for MASW, the more injection points you have, or the wider you go, the more resolution you get, the more depth you can identify and survey. So by having more injection points, we're able to look at a much wider area. And because we're looking at a much wider area, the currents are also looking at a much deeper area too. If you were to bring those injection points closer together, or you had less injection points, you get a much shallower section you're looking at, or a much narrower section. So we can span our survey size or depth or consideration by spacing out, pulling apart, or pulling together our probe sensors. So if you happen to look at 2 or 3 miles of alignment and you have a limited amount of investigation dollars, you may look at doing it at a much wider spacing. The resolution may not be as high, but you can then come back and focus your investigation on where it needs to be focused. So you can do a quick broad brush screen before you start your work. Similar to MASW, we commonly use this for 50 to about 100-foot depth. They can go deeper than that as well. It's slightly more expensive than MASW, and the reason for that is because MASW tends to have less equipment being used, and the ERI tends to have a little more equipment. You're carrying a little more information. You're looking at more data processing, so the cost tends to be a little bit higher. But dollar for dollar against the soil boring, the cost to mobilize a drill rig, to bring an engineer on site, to do a lab testing, we've noticed that MASW and ERI still tends to be a cheaper and faster way of doing that investigation. So it tends to be a much quicker way and a little bit cheaper way of investigating this ground risk. So MASW is typically used for looking at shallow rock, quick screening the ground profile. Where we see electrical resistivity tomography or imaging used as being used for geologic hazards, things like karst and sinkholes, things like open mines or open voids, water-filled voids or air-filled voids, looking at ground seeps on steep slopes and those sort of things. So MASW is used best for rock reparability, depth of rock, quick ground profiling. ERI is the more robust tool used for identifying sinkholes and mines and ground challenges. So we use it quite often for, again, caves, solution sinkholes. We can use it for depth to bedrock, but MASW is better because we also get that shear wave velocity. And that shear wave velocity is helpful, as I mentioned before. You have that rippability chart. Because you're measuring a physical parameter of the rock, you're actually measuring how rippable is that rock as well. You don't get that same measurement when you're doing ERI. So we tend to look at MASW for the shallow rock and ERI for more of the voids and sinkholes and those sort of things. And like seismic, the electrical method can do a one-dimensional, just one location where that probe's done, a 2D profile, or a 3-dimensional if you happen to have a volume image. You did more than one, you did this survey on a hash pattern. So instead of doing single lines in parallel, you do a line in perpendicular to the parallel lines. And there's a great question that's being asked by Melanie. What areas in the US seem to be the area that ERI is most important? Well, as I mentioned before, ERI is used very often for things like karst and sinkholes. So where you happen to have karst, areas like Pennsylvania, Ohio, West Virginia, where we see a lot of this shale being collected. Areas also like Illinois, in Pennsylvania particularly, and Virginia, you might have former mined areas. Things like anthracite coal might have been mined from those locations. So ERI tends to be most important in these northeastern states where karst is very applicable. Also in the states like Florida and the South. So wherever you end up having limestone, dolomites, and have concerns for sinkholes, that's a great location where ERI is really important. Hopefully that answers your question, Melanie. So like MASW, here's another cross-section of what this profile looks like. You're seeing another colorful image in front of you. And this colorful image is showing you the same sort of thing. It may look like Greek to you before. What you're physically seeing here, though, is a color spectrum that shows different resistivities. The higher resistivities go for things like gravel and hard rock. They also go for some of the larger void caverns, and the smaller tends to be for the wetter materials, the clay materials, also the water-filled materials that we have there too. So what we see here is by doing an electrical resistivity survey, you see this stock image here showing you this deeper soil-filled channel, and it's soil-filled because it's filled in with blue, some of the wetter and softer material. You then have this top of rock, this nice dark material. And this little dip here, you start seeing a weathered rock channel. There may have been a remnant stream here coming through at some point in time, or if it's much deeper, a sinkhole. As the sinkhole is opening up, it's creating this bowl structure, this open void at the top that's causing the bedrock to sink in. And you get the suspected bedrock channel there too. So another slice of this, what you see at the top is what would have been a ground surface cut. So we've traced the top of rock in there with this yellow dotted line. You can see the soil-filled voids in this yellow dotted line there. And if I were to take the ERI survey at the very top of this location and go across this area to about 50-foot length, what I find here is not an exact sort of line the way that we see it up top. We trace this yellow dotted line as a purple dotted line here on the bottom image. But what you do notice is that ERI did pick up, in almost all cases, you had this anomaly here of softer soil-filled area in blue. You had a hard nub there of rock in red. Then again, you had this soil-filled area and this blue channel, a redder area there for that more Compton rock. Then soil-filled void, some rock, void again, back to rock again. So it's giving you some idea. And the idea here is not to give you a precise depth of rock or a precise top of this channel. What you're looking at again, and what we're trying to explain here is geophysics is a good tool in your toolbox to help you identify where is there ground risk. If there's no ground risk here, we don't see any karst issues, we don't see any shallow rock issues or areas that need to be ripped out. We can then screen past this and investigate another location instead. So from here, we're seeing that we do have some solution voids. This typically is called pinnacle karst. And in pinnacle karst, you see this sort of undulating top of rock surface that could have been dissolved over time. And this is identifying the fact that we have pinnacle karst across this location. So here's a project in Pennsylvania where it's karst country out there. We're lucky that Pennsylvania, the DEP, has mapped, along with Virginia and a lot of different states that have karst, has mapped the location of sinkholes and also locations where former mines and areas may have been. So we know we happen to have a portion of site where the project site's going through. We know we have a likelihood of pinnacle karst. We can see from the mapping here, the dotted yellow dots that we have, and the orange dots show map depressions. The green dots actually show physical map sinkholes that PADEP has identified and remediated over time. And we see also that we have done these electrical resistivity imaging lines across the property. Now, trying to investigate this site and investigate this many sinkholes across this area may become a difficult and challenging, sometimes even costly process here. So because this is a 35-acre site, we only had about a day and a half worth of time to do investigations. We want to focus our dollars across where the actual pipe alignment was going to go. And once the alignment's being put through, then along those alignments, do we have concerns of karst and caverns? Should we shift the pipeline? Do we have sufficient bridging capacity for that pipeline? Or do we need a more robust solution such as piles, cradling, grouting, etc.? So what we tend to find is our ERI is giving us this sort of cross-section. And from this cross-section, we can glean a couple things. So from 0 to 1650, or almost a quarter mile, was done in about a day's worth of time. What we see is this upper zone here, greens and blues, then I guess there's darker zones of reds and yellows. Traditionally, Pinnacled karst means that the karst top surface, or the top of rock surface, tends to have pinnacles to it, right? Up and down areas across the top of the rock surface here. So what we see is historically at around elevation 380 on the left-hand side, that's where top of rock may have been. And you see some areas as they dip down along the alignment at around 550 or 600 feet to about 900 feet, it dips down significantly. And you see that dip because the top of the rock surface, that red material there, that harder material, that red drops down off the paper, comes back up again around 900 to 1150. It dips again, comes back up around 1250, all the way over to 1650 there. And what we're finding here is in this zone from 600 to 900, you had a sinkhole. And over time, that sinkhole may have formed, the sinkhole collapsed, and soil filled in that zone. That's why you see this missing section of that red zone, that rock. So we call that a sinkhole, and that sinkhole throat has been filled in with soil. Same thing happened around 1150 to 1250. You had a sinkhole open up, it collapsed that rock bridge there, it filled with the soil, and you got this rock next to it. On the right-hand side, from 1250 to 1650, you see another small void zone being developed inside that rock area. Now you have two options here. If the pipeline has sufficient capacity to bridge that area, it's either the sinkhole is deep enough or the pipe can span far enough across this size sinkhole being 250 feet, linear feet, then there may not be a concern. But if we see this sinkhole opening up over time, if the sinkhole were to open, the potential void size could be as large as 250 feet. Now that we've identified over a 1,300 foot long or 1,600 foot long swath in one day, we would then tend to go do a boring at the location where the sinkhole exists to physically proof out the geophysics that we actually have done. So one of the questions Russ asked before is, what's the limitation of geophysics? The limitation is this: we haven't gone out there and physically confirmed that sinkhole is there, it's a certain size, and the rock is not strong enough to bridge that sinkhole. So now that we identify within the day where these concerns might be, now we'll go focus on doing our physical soil boring, our rock coring, our lab testing to make the engineering decisions that we need to mitigate that risk. So our first pass and screen was to do our geophysics. Then we came back in, we did our investigation technique. Now we've identified locations where we have this concern. On the left-hand side, what you see is two white open areas. Now those white open areas don't necessarily mean it's a massive open void. It could point to a void. It could also point to what's called shadowing. And in shadowing, what tends to happen is the geophysical technique may find a boundary. The boundary goes from a very high resistivity to a low resistivity, or vice versa. It may also go from a high shear wave to a very low shear wave, and that boundary might cause a reflection, and that boundary may not pick up what's underneath that reflection there. So what you tend to see here is you tend to see a potential anomaly here. It may need to be investigated by doing a boring or test pit or another technique there. So in this case specifically, we need to go out there and do additional investigations. But this quarter-mile alignment was looked at in a matter of a day and a half, which helps us then focus our investigation dollars. We can do the same thing if we're looking at fractures and voids, looking at where we have concerns, and just another picture for us to look at of what these sort of techniques show us and what they resolve for us. As I mentioned also, the ERI technique is just a 4-point winner technique, what we use for grounding design on steroids. So we can use that 4-point winner, or we can use this 96 probe electrode probe sensor and actually pare it down to a 4-point winner and collect the information that we need to do our traditional grounding design. So it's also used for that purpose as well. I mentioned a more boutique technique, which is the microgravity. So ERI and MASW are used great when you happen to have, not really a lot of background noise, not a lot of obstructions. But if you're working in a very urban area and you happen to have buried cables, overhead transmission lines, roads nearby, a lot of vibrations happening from background, you will get a lot of false positives in those techniques. So things like microgravity, which are a lot more expensive, can come into play. Microgravity is used very often by measuring the variation in density, right? Different materials have different gravitational pulls to them based off their density. So you're looking at the density material contrast. If something is more dense than another or less dense, if you happen to have an open void, less density in that void than you happen to have in that small grain of soil or rock or gravel, for instance. You're measuring that contrast of density between two different things. They're great because they're unaffected by electrical noise, by vibrations and traffic and utilities, but they're a lot more costly. And the idea to get resolution requires things like LiDAR surveys and topo being done. That way you can tie the actual microgravity results to an actual depth to bedrock or depth to your anomaly. You can see here that a lot of these techniques are more costly, but they give you a little bit different resolution. This is being done here to look at ERI for a site. This technique is looking at the density and gravity. We're able to map it using topo, which gives you the ground surface. We're also looking at the depth and gravity change at a series of points. By putting those two meshes together, draping the topo over the actual depth to our anomaly, we can get the location where our anomaly may exist, which helps identify where you might have concern areas. And then, like I mentioned before, you may go in and do traditional investigation techniques, things like soil borings, test pits, and so on, to identify your areas of concern. Right, and similar to our MASW and ERI, we get a cross-section, we get something we can look at, which helps us identify what this cross-section might look like for our subsurface condition. I want to quickly talk about GPR because GPR is something that's used very frequently. It can be used for things like locating shallow rock, but GPR is based on the concept of radar. Radar has electromagnetic energy, and you're measuring the actual amount of energy transmitted to the ground. If the energy hits something like a buried object or a boundary like a depth of rock or a hardened material, the energy against that material then is reflected, refracted, or scattered back to the receiving point where the energy is being put. So if you happen to have rock, if you happen to have an underground storage tank, you happen to have a underground utility, that utility or that boundary might reflect back the energy you have, and as it reflects back, it's picked up by the sensor. Now, how much energy gets down to the ground, this sort of lawnmower looking object here, that's our geophysical GPR equipment. It only has a certain amount of fixed energy to it. So a material that happens to be more dense, happens to be wetter, for instance, like clay or silt, those types of materials tend to be sinks for energy. And by sinks, I mean something that actually pulls in the energy and actually removes energy from the source. If you happen to have something like sand or gravel, they allow the energy to pass through more freely. So in different types of soil, you have different depths as to how far this can look. So in the case of looking at shallow bedrock, GPR might be useful because shallow bedrock, you might be looking at 0 to 10 foot. In that case, GPR might be good. But if you're looking for things like sinkholes, if this is only looking at 0 to 20 feet below your ground surface, and you happen to have a large sinkhole at 25 to 30 feet below your ground surface that covers a much larger area, that's a concern you may have missed using GPR techniques. So I want to be careful that I also talk about the limitations of geophysics and GPR. And GPR particularly, the depth at which you're looking at is limited by the depth of the energy of the equipment. In most cases, we're using equipment that's carried out in the field, being used by field technicians. In that case, that depth is usually around 7 to 15 feet. I've seen it go as deep as 25 feet. Beyond that, though, the accuracy drops quite a bit. It's not as useful for detecting geologic voids, again, things that are deeper, because if they're deeper and they're wider, even though you might detect a 2-foot diameter sinkhole at 5 feet below ground, there might be a much bigger sinkhole beneath the ground surface that creates more risk and more concern for your pipeline that needs to be looked at. So GPR may not be the right technique. ERI or ERT might be the right technique for you. It is a lot cheaper than MASW and soil borings and ERIs, but again, the cost also comes in with the information that you get. MASW may be more expensive, but you get more information like rock rippability, depth to bedrock, material properties that you can use for engineering design, and GPR, you don't typically get that information. You see it used quite a bit to locate anomalies. If you're looking at buried utilities, looking at things like underground storage tanks or former buried objects, GPR can be a great use for that, but we typically see it being used a lot more for utility location than we do see it used for mapping geologic voids, finding depth to bedrock with accuracy, understanding rock rippability, and those sort of things. So again, being used a lot more for that underground utility mapping. So I do want to go through just one last caveat here as we talk about geophysics. You heard me discuss that geophysics is more of an indirect, non-invasive method of investigation, meaning we're measuring things using correlations to density, the electrical resistivity. And even those correlations can help us identify strength of rock, rippability of rock. Calibrating that information is obviously necessary and paramount. And calibrating it means trying to have a test pit or a soil boring, something that's actually invasive that you can do next to or adjacent to the geophysics that you've done to make some sense of the data. So if you find out that you've had a shear wave velocity of 200 foot per second or 2,000 foot per second, doing a soil boring along the location gives you a sense of, well, the 200 foot per second information was silty sand with a blow count of 8 to 12 blows per foot. And the 2,000 foot was actually some of the harder shale rock that we had across the site. That information can't be calibrated unless we actually do a physical investigation technique like test pits or soil borings. So I'll always say that it's good to calibrate the information you get from geophysics. Don't forget also that we may be needing to use our traditional SPT, soil borings, our test pits, because designers, vendors, third parties still may require us to have these SPT flow counts, the end values, for rule of thumb foundation design, for actual deep foundation design, for cut and fill analysis, to see if we want to reuse material types, right, to collect a sample, to do grain size and proctor testing on it for compaction and reuse. So you might still have to use traditional investigation techniques. The analysis is only as good as the experience of the professional reviewing the data. So if you happen to have geophysical equipment, you happen to do GPR, it's great. As you see here, you can make some sense, and hopefully you're dangerous after this presentation to make some sense of what that colorful two-dimensional cross-section looks like. But it's still important for a professional to look at the information and make sense of what that is showing us, where the risk might be in the subsurface. Once you identify that risk, again, risk management means you're transferring the risk to another phase of your work. You want to make sure you identify the risk and then try to address it later on in your project. And keep in mind that building codes and agencies may still require conventional techniques, even though you've done geophysics for karsts or sinkholes, shallow mines, shallow bedrock. You may still need to fulfill the agencies and building code requirements for conventional investigation techniques. And lastly, again, you might still have to do investigation techniques to collect samples for actual constructability. What's the thermal resistivity of this material? Can we use material for cut and fill analysis? Is the soil expansive? Is the soil collapsible? Things that are really important when it comes to our design of foundations. So with that, I just want to thank everyone for your time. And if you have any questions, I'd be glad to go through them. I really appreciate the opportunity, Russ, here and the whole SparkCon team to present this information. And hopefully it's helpful and gives us some more tools in our toolbox to manage ground risks and, again, improve our investigation techniques.
And we want to thank you, Dr. Shah, for all of the information that you shared with us. It's really one of those opportunities that a lot of people don't have, and to be able to spend time with you. I know you're a professor at 2 universities, 2 institutions. Remind us which ones where you're going to be found at.
NJIT, which is my alma mater,
okay, all right.
And also at NYU.
Awesome. And also, I want to make sure that people understand that this is an evolving, expanding discipline, and from people that are learning and you're educating along the way, this is exciting information to be able to use in your organization and learn a little bit about how you can remove risk from your future projects, and also how you can contact people and make sure that there's an opportunity to investigate these things. What are some of the more challenging areas that you see that are kind of being brought to the market today for future business
Sure.
and projects?
So obviously one of our most challenging types that we use this for are things like horizontal directional drilling, right? With HDD investigations, you're putting a pipeline under a sensitive crossing. In most cases, we do one boring on either side. And the concern of an inadvertent return from an HD gone wrong can be pretty significant. So using things like geophysics and implement them now into our risk management strategy helps us make better decisions. We actually had a project just recently in Pennsylvania through a former mined area where we had to cross 2 highways, an 8-lane highway. Underneath the highway was a shallow bedrock area. Under that was a 15-foot thick coal mine that was mined back in the late 1800s. That was almost a no-go for us for HEDs, and it was almost looking at cut and cover traditional investigation and traditional installation of the pipeline. But by doing some geophysics, we're actually able to thread the needle and find a location that we could have actually put the HED through the shallow rock above the mine to avoid that potential inadvertent return. Because the consequence, both cost, schedule, environmental, would have been significant, and the cost to go out and investigate that using just hundreds of borings to close a highway to investigate would have been substantial. So we're seeing the challenges being met by tools like geophysics to help reduce risk for things like that for oil and gas.
And I know that some of the technology that you've used has been expanded beyond oil and gas industry, and it's really enlightening to see how just under the surface life can be in some of the formations and things that are taking place as you go through and expand there. Any interesting caveats that we want to recommend that people look at as they reach out and get a hold of people like Mott McDermott and the team over in your place?
Sure. I mean, Mott McDonald has always been fantastic in doing geotechnical investigations and geophysics. I represent the energy practice lead for geotechnics in Mott McDonald, but I'll always say the information you collect is only as important as the person identifying the information. My dad is also an engineer, would always say that you can go to CVS and buy a stethoscope. Didn't ever make you a doctor, though. You still have to have the right professional looking at those concerns, because ground risk can become a very challenging thing.
Yeah.
So to make sure you have the right professional looking at it, whether it's Mott McDonald or anyone else, can really help you make better sense. So you spend your dollars more wisely and you minimize the risk you have with your schedule.
I like that. I like that philosophy of, let's invest in the higher risk areas to remove that risk from the project, and then do some investigation across all levels of the project. And it pays to have an experienced engineer take a look at that and investigate some of the things that you might be concerned about or might be wondering about just under the surface. So thank you so much for being here. Really appreciate the opportunity. SparkCon 2020 will be available and expanding on these topics all week long. We've got several topics involved in the oil and gas industry, and some of the things that you need to be aware of as we grow and expand our business and remove our risks and work towards being successful. So thank you, Dr. Shah. I really appreciate your help and opportunity to be here. Any last words or recommendations if people are wondering what might be right for them and how they can operate in the future?
I would say reach out to a good professional. My information is available at this point in time, but this is only the tip of the iceberg, right? Managing ground risk can become a big thing. Hiring the right person up front really helps manage that risk.
Well, thank you so much for being here. Appreciate it. And if you have any questions, it looks like we lost Dr. Shah. The internet held on for quite a while. He's coming back. Vatsal, thank you so much for hopping back in here. Looks like it's amazing that in this 2020 and so all of the challenges that we have, this is the kind of information that we want to bring to the table for you in the industry, everybody that's working towards being successful, navigating these challenges and these challenging times. It's really a part of the journey that we're taking all together and making sure that we have the tools and the opportunities to see what we can do, navigate the challenges, and increase and improve our business goals. So I wanted to thank you so much for the opportunity to be here, and tune in, sign up, register for future episodes for SparkCon 2020. And we look forward to seeing you in the next scheduled event. I'm Russ Johns. Thank you so much for being here, and you enjoy the day. Take care, everyone.